A sequence of satellite images began to circulate among monitoring teams, not because of a sudden crisis but because of a pattern that refused to stay subtle. Bands of color, repeating, layered, almost hypnotic, were spreading across the summit region of Kīlauea. Each band marked movement, not in meters or even in dramatic shifts visible to the eye, but in increments so small they would normally escape attention. Yet those increments, measured precisely at about 2.8 centimeters or roughly 1.1 inches per color cycle, were stacking. The question that emerged was not whether the volcano was moving, but how much motion was being quietly accumulated, and what that motion revealed about the processes unfolding beneath the surface. Why would a volcano repeatedly shift by such a specific amount during eruptive activity? What mechanism produces these consistent increments, and why do they appear as layered fringes instead of a single measurable change? If each band represents only a fraction of the total movement, how large is the full deformation during an eruption cycle that spans days or even weeks? And perhaps more importantly, what does that motion indicate about the behavior of magma reservoirs that cannot be directly observed? The images originate from a technique that has reshaped how volcanic systems are monitored. Known as interferometric synthetic aperture radar, or INSAR, it relies on radar signals transmitted from satellites orbiting far above Earth. These signals bounce off the ground surface and return to the satellite, carrying phase information that can be compared over time. When two images taken at different moments are combined, even minute changes in the distance between the satellite and the ground surface become visible. The result is not a simple before and after picture, but a map of deformation encoded in repeating color patterns. Each of these patterns, referred to as fringes, represents a fixed amount of motion along the satellite's line of sight. At Kīlauea, that increment has been calibrated to approximately 2.8 centimeters or 1.1 inches. The precision of this measurement is not an estimate, but a direct consequence of the radar wavelength and the physics of interference. When the phase difference between two signals completes a full cycle, it corresponds to that specific displacement. As a result, a single fringe does not signify the entirety of ground movement during an eruption. Instead, it acts as a unit marker, a measurable step in a larger sequence. When multiple fringes appear across an image, the interpretation changes significantly. 5 fringes correspond to roughly 14 centimeters, or about 5.5 inches of displacement. 10 fringes extend that to approximately 28 centimeters, or near 11 inches. In some eruptive episodes, the number of visible fringes expands beyond these counts, indicating cumulative deformation that reaches into several tens of centimeters. The key detail is that the 2.8 centimeter value is not the total movement per eruption, but the scale of each incremental band. This distinction matters because it reframes how volcanic deformation is understood. A casual reading of the measurement might suggest that each eruption produces a modest shift, barely more than the width of a finger. The INSAR data contradicts that impression. The repeated stacking of fringes reveals that the ground can move far more than a single increment, with deformation unfolding gradually as magma migrates beneath the surface. The apparent subtlety of each fringe masks the larger scale of motion taking place over time. At Kīlauea, this motion is closely tied to the behavior of its summit magma system. Before an eruption begins, magma accumulates within subsurface reservoirs, increasing pressure and causing the ground above to inflate. This inflation is not uniform, it spreads outward from the source, creating a broad uplift that can be detected by satellite radar. As the eruption progresses, magma drains from these reservoirs toward the surface or along rift zones, reducing pressure and leading to deflation. The ground subsides, again in a pattern that is captured as a series of fringes. The cycle of inflation and deflation is not new, but the clarity with which it can now be observed represents a shift in monitoring capability. The United States Geological Survey has documented multiple eruptive episodes between 2024 and 2026 in which these deformation patterns appear consistently. The images show concentric or elongated bands centered around the summit, each band marking another increment of movement. The spacing and number of fringes vary from one episode to another, reflecting differences in magma volume, pressure changes, and the geometry of the subsurface system. One of the more revealing aspects of these observations is the spatial extent of deformation. The fringes are not confined to a narrow zone, but often spread across a wide area surrounding the summit caldera. This indicates that the underlying magma chamber is influencing a large area of the crust, not just a localized point. The deformation can extend several kilometers, equivalent to a few miles, suggesting that the processes driving the motion operate on a scale much larger than the visible eruption site. The timing of these changes also provides important context. Rather than occurring instantaneously, the deformation unfolds over periods ranging from several days to a few weeks. This gradual progression aligns with the dynamics of magma movement, where pressure builds and releases over time rather than in a single abrupt event. The INSAR data effectively captures this temporal evolution, with successive images showing the accumulation or reduction of fringes as the eruption cycle advances. Another layer of complexity arises from the directionality of the measured movement. The 2.8 centimeter increment corresponds specifically to displacement along the satellite's line of sight, not necessarily vertical motion alone. This means that the actual ground movement may include both vertical and horizontal components. In some cases, the ground may be uplifting while also shifting laterally, a combination that reflects the three-dimensional nature of magma intrusion and withdrawal. Understanding this distinction is critical when interpreting the magnitude of deformation. A single fringe might represent a combination of upward and sideways motion that together produce the observed change in distance from the satellite. As a result, the total displacement of the ground surface can differ from the line of sight measurement depending on the geometry of the movement. This adds another dimension to the analysis, requiring careful consideration of viewing angles and deformation vectors. The consistency of the fringe scale, however, remains a reliable anchor. Each band represents the same increment, allowing scientists to count fringes and estimate total deformation with a high degree of precision. This repeatability is what makes INSAR such a powerful tool for monitoring volcanic systems. It transforms subtle shifts into visible patterns, enabling the detection of changes that would otherwise go unnoticed. At Kīlauea, these patterns have revealed a system that is continuously adjusting, even between more visible eruptive events. Inflation phases can occur without immediate eruption, indicating that magma is accumulating but has not yet found a path to the surface. Conversely, deflation can follow an eruption as the system rebalances. The interplay between these phases creates a dynamic environment in which the ground is rarely static. The implications extend beyond the measurement itself. The ability to track deformation at this level of detail provides insight into the volume of magma moving within the system. Larger numbers of fringes generally correspond to greater changes in pressure and volume, although the relationship is influenced by factors such as chamber shape and rock properties. By analyzing these patterns over multiple episodes, it becomes possible to identify trends and variations that might not be apparent from a single event. The images from 2024 through 2026 illustrate this variability. Some episodes display tightly spaced fringes concentrated near the summit, while others show broader distributions extending outward. The number of fringes can differ significantly, indicating that not all eruptions produce the same magnitude of deformation. This variability underscores the importance of viewing the 2.8 centimeter increment as a unit of measurement rather than a fixed outcome. Another notable feature is the clarity with which deflation signals appear during eruptive activity. As magma exits the summit reservoir, the decrease in pressure leads to subsidence that is captured as inward-moving fringes. These patterns often dominate the imagery during active phases, highlighting the areas where the ground is sinking relative to its previous state. The extent and speed of this deflation can provide clues about the rate at which magma is being drained. The broader context of these observations lies in the integration of satellite data with other monitoring methods. While INSAR provides spatially detailed maps of deformation, it is complemented by ground-based instruments that measure tilt, seismic activity, and gas emissions. Together, these datasets create a more comprehensive picture of volcanic behavior. However, the satellite perspective offers a unique advantage in its ability to cover large areas consistently over time. As the sequence of images continues to grow, the pattern becomes harder to dismiss as a minor detail. The repeated appearance of fringes, each marking the same incremental movement, forms a record of the volcano's internal adjustments. It is a record that does not rely on dramatic eruptions or visible lava flows, but on the quiet shifting of the ground above a restless magma system. The focus on a value as specific as 2.8 centimeters might seem narrow at first glance, yet it serves as a key to interpreting a much larger process. By understanding what each fringe represents, it becomes possible to decode the layered patterns and estimate the total deformation associated with each eruptive episode. This, in turn, provides a window into the volume and dynamics of magma movement beneath Kīlauea. The question that remains is not whether the volcano moves by this amount, but how often those increments accumulate, how they differ from one episode to another, and what they reveal about the evolving state of the magma system. The fringes continue to appear, each one a small but measurable step in a process that unfolds far below the surface, building a detailed map of movement that extends beyond any single eruption. The accumulation of these measured increments begins to take on greater significance when viewed across successive eruptive episodes rather than in isolation. A single sequence of fringes may outline one stage of activity, but when multiple events are compared, a broader pattern emerges in how Kīlauea redistributes pressure within its system. The deformation is not random, nor does it reset entirely after each eruption. Instead, it reflects a continuous adjustment of magma reservoirs that expand, contract, and shift in response to changing internal conditions. Satellite records spanning several years show that inflation phases can rebuild gradually after a deflation event, often restoring much of the ground displacement that was lost when magma drained during an eruption. This reinflation may occur over weeks or months, depending on how quickly magma is resupplied from deeper sources. The pace is not constant. Some intervals show steady uplift measured in multiple fringes accumulating over a relatively short period, equivalent to several centimeters or a few inches of vertical and lateral change combined. Other intervals display slower growth, with only one or two fringes forming across the same time frame. This variability points to differences in supply rates beneath the summit. Magma does not rise in a continuous, uniform flow. It pulses, stalls, and occasionally redirects. When supply exceeds outflow, pressure builds and the ground swells outward. When outflow dominates, the system deflates. The INSAR fringes capture these shifts with a precision that allows even modest imbalances to be detected. A cluster of 3 or 4 fringes appearing over several days corresponds to roughly 8 to 11 centimeters, or about 3 to 4 inches, of movement along the satellite's line of sight. Spread across a wide area, that change signals a measurable alteration in the volume of the underlying reservoir. The geometry of the deformation provides additional clues. Circular or elliptical fringe patterns centered on the summit suggest a relatively symmetric source, often interpreted as a pressurized chamber or a group of connected reservoirs at depth. Elongated patterns extending along known structural directions indicate that magma is moving laterally, possibly feeding rift zones that branch away from the summit. These directions are not arbitrary. They follow pre-existing weaknesses in the crust, guiding the path of magma as it seeks routes of lower resistance. Over time, repeated cycles of inflation and deflation leave a signature that can be compared across different eruptive episodes. Some sequences show nearly identical fringe configurations, implying that the same parts of the magma system are being pressurized and drained in a consistent manner. Others diverge, revealing shifts in where magma accumulates or how it migrates. The differences may be subtle in a single image, but become more apparent when several cycles are examined side by side. The role of the United States Geological Survey in documenting these changes has been central to interpreting what the fringes represent. By maintaining a continuous record of satellite observations and correlating them with ground-based measurements, a clearer picture has emerged of how deformation relates to eruptive behavior. The fringes are not mere visual artifacts. They are quantitative markers that can be counted, mapped, and compared with other indicators such as seismic tremor or gas release. One of the more revealing aspects of the data is how deformation extends beyond the immediate vicinity of visible lava activity. During some eruptive phases, the most pronounced deflation is centered at the summit, even when lava outflow is occurring at a distance. This indicates that the summit reservoir remains a primary source feeding the eruption, with magma traveling through subsurface conduits before reaching the surface. The loss of pressure at the summit is then recorded as a series of inward-moving fringes, each representing another 2.8 centimeters or 1.1 inches of decrease in the line of sight distance. In other cases, deformation patterns shift toward the flanks, suggesting that magma is being stored or transported outside the central chamber. These episodes may produce fringe distributions that are offset from the summit, highlighting the areas where pressure changes are most pronounced. The ability to detect such shifts is particularly valuable because it reveals processes that are not directly visible. A site that appears quiet at the surface may still be undergoing significant deformation beneath. The cumulative effect of these small increments becomes especially important when considering the total volume of magma involved. While each fringe corresponds to a fixed displacement, the area over which that displacement occurs can be extensive. When multiple fringes cover several square kilometers, the implied change in subsurface volume becomes substantial. Translating fringe counts into volume estimates requires additional modeling, but the relationship is clear. More fringes over a larger area generally indicate a greater quantity of magma movement. Temporal resolution adds another layer of insight. Satellites do not capture continuous video, but rather snapshots taken at regular intervals. By comparing images separated by a few days or a couple of weeks, it becomes possible to determine how quickly deformation is occurring. Rapid accumulation of fringes suggests a faster rate of magma intrusion or withdrawal, while slower changes indicate a more gradual process. These rates can vary not only between eruptions, but also within a single episode, reflecting shifts in the dynamics of the system. The interpretation of line-of-sight displacement remains a critical consideration throughout this analysis. Because the measurement depends on the angle between the satellite and the ground, the same physical movement can produce different fringe patterns depending on viewing geometry. To address this, data from multiple satellite passes, often from slightly different angles, are combined. This allows the separation of vertical and horizontal components, refining the understanding of how the ground is actually moving. Despite these complexities, the core measurement retains its clarity. Each fringe equals 2.8 centimeters or 1.1 inches of motion along the line of sight. This consistency provides a reliable scale against which all deformation can be assessed. It is a fixed reference in a system that is otherwise highly dynamic. The broader significance of these observations lies in how they redefine the scale at which volcanic movement is perceived. Rather than focusing solely on eruptions as discrete events, the INSAR data emphasizes the continuity of deformation before, during, and after visible activity. The volcano is in a constant state of adjustment, with magma shifting beneath the surface, even when no lava is erupting. The fringes record this ongoing process, capturing both the buildup and release of pressure over time. Patterns observed between 2024 and 2026 illustrate this continuity. Episodes labeled sequentially show deformation beginning prior to eruptive onset, intensifying as magma rises, and then reversing as the system deflates. The number of fringes associated with each phase varies, but the sequence remains recognizable. Inflation produces outward-moving bands, deflation draws them inward, and the transition between the two marks a change in the balance of forces within the magma system. The persistence of these patterns suggests that the processes driving them are deeply rooted in the structure of Kīlauea itself. The volcano's plumbing system, composed of interconnected reservoirs and conduits, governs how magma is stored and transported. Changes in one part of this system can influence others, leading to deformation that extends across a broad region. The fringes act as a surface expression of these internal connections, mapping out the areas where pressure changes are occurring. As more data accumulates, comparisons across longer timescales become possible. Subtle shifts in the center of deformation, variations in fringe density, and changes in the speed of accumulation all contribute to a more detailed understanding of how the system evolves. These observations do not point to a single uniform pattern, but rather to a complex interplay of factors that shape each eruptive episode. The focus on a seemingly modest increment, 2.8 centimeters or 1.1 inches, ultimately serves as a gateway to interpreting much larger movements. Each fringe is a unit, but the sum of those units reveals the full extent of deformation. Whether the total reaches a few centimeters or several tens of centimeters, equivalent to a few inches or more than a foot, depends on how many fringes appear and how widely they spread. By continuing to track these patterns, the changes within Kīlauea's magma system can be monitored with increasing precision. The repeated cycles of inflation and deflation, captured in successive bands of color, provide a record that extends beyond individual eruptions. It is a record built from incremental measurements, each one small on its own, yet collectively mapping the movement of a volcanic system that is constantly reshaping the ground above it.